The first thing the river takes from you is clarity. Under the dense Amazon canopy, light breaks apart into drifting fragments, never reaching the bottom in one piece. The water becomes a vessel for shadows rather than reflections, carrying the smell of rotting leaves, dissolved soil, and the faint metallic taste of distant storms. Out here, even on a perfectly windless day, the water feels charged, as if it remembers things that moved through it. This is the domain of the electric eel, a creature so often mislabeled that even its name hides the truth. It is not an eel at all, but a knife fish, a member of a lineage shaped by darkness, sluggish water, and the constant need to sense rather than see. Evolution sculpted its body into a long, flexible conductor, a living battery layered with 3 electric organs stacked like biocapacitors along its flank. Inside these organs, specialized cells called electrocytes lie in neat arrays, each one a tiny biological switch that can flip from neutral to full polarity in milliseconds. A single cell offers almost nothing, barely a flicker of charge, but thousands firing in perfect sequence create a pulse strong enough to ripple through an entire riverbank. Voltage is the height of the electrical wave, current is the mass behind it, and the eel wields both. With brief staccato bursts around 50 volts, it maps its surroundings the way a bat uses sound. With heavier volleys reaching several hundred volts, it turns that quiet, probing language into a weapon. These pulses aren't random. In the murky shallows where visibility collapses to centimeters, the eel builds a mental image of the world through distortions in the electric field. Each lily stem, each drifting fish, each submerged root produces a signature. When prey shivers nearby, a small twitch of muscles beneath scales or skin, the eel doesn't just detect it, it reads it. This electroperception is what transforms a blind moment into the beginning of a hunt. And when the eel locks onto a target, its entire body becomes an amplifier. The first shot is almost polite, a rapid pair of quick taser-like bursts. The double tap races through the water, forcing all nearby muscles to contract. Small fish respond instantly. Their bodies freeze, then jolt upward like marionettes with severed strings. The eel uses this reflex as a locator, tracking where the involuntary twitch originated, then lunges with an explosion of current that can overpower animals far larger than itself. These longer volleys, lasting fractions of a second, don't just stun. They override neuromuscular control entirely. A creature hit by that wave loses ownership of its own body, and this is where a human enters the story. Imagine someone wading through water the color of brewed tea, a fisherman retrieving a tangled net, a traveler crossing a shallow channel to reach a dry patch of forest, or a local accustomed to these rivers and confident in their rhythm. The bottom feels soft, a mix of clay and decomposing vegetation, and the water pulls around the legs with gentle inertia. Nothing warns them. Electric eels do not surface with dorsal fins or swirling patterns. They rise quietly, sometimes brushing against the skin without revealing intent. Their camouflage is anonymity. The first shock hits like a mistake, a jolt through the calves, a sudden tightening of the muscles, an instinctive gasp. The body tries to rationalize it, a cramp, a stumble, maybe a submerged root. But the second pulse arrives before the thought is complete. It clamps the diaphragm, locks the abdominal muscles, and sends a sharp metallic taste up the throat. The victim tries to inhale and finds the chest frozen mid-motion. The legs attempt to step backward, but instead jerk forward, betraying their owner. The river swallows balance with the same ease it swallows stones. Once in deeper water, the danger multiplies. The eel fires again, not out of malice, but confusion. In the chaos of stirred sediment and thrashing limbs, the human reads as a large, persistent threat, something to be neutralized. Each volley is a command the nervous system cannot ignore. Hands seize, fingers curl, the back arches. Every involuntary contraction pulls more air from the lungs without allowing any to return. The victim sinks not because they are heavy, but because their muscles refuse to coordinate the simple act of staying upright. Drowning, in this context, becomes a mechanical inevitability. The mouth slips beneath the surface. The river presses in. Water fills the nasal passages, triggering a desperate urge to inhale, but the diaphragm's paralysis holds that breath hostage. When it finally releases, the attempt to breathe becomes the act that ends it. Water rushes in, sealing the lungs with fluid that blocks oxygen exchange and collapses precious alveoli. Even if the eel stops firing, the damage is already unfolding inside the chest. Most fatalities attributed to electric eels are not electrocutions in the classic sense. The electricity rarely stops the heart. Instead, the river delivers the finishing blow. The eel provides the paralysis. The water provides the burial. And because these incidents often occur in remote areas, without witnesses or immediate rescue, the outcome is bleak. A stunned swimmer lasts seconds. A resuscitation attempt requires minutes. The math does not favor survival. Yet in the hierarchy of Amazonian dangers, the electric eel does not sit with the infamous executioners. It is not the jaguar with its bone-crushing bite, nor the bushmaster whose venom can unravel a bloodstream, nor the anaconda whose coils shut down circulation with frightening efficiency. The eel kills by circumstance, not aggression. Its shocks are tools for hunting and self-defense, not predation on humans. Most encounters end with nothing more than a shocking memory and trembling limbs. But danger is contextual. In shallow water with friends nearby, the risk is low. Alone in a deep channel, tangled in roots, stepping unknowingly into the eel's hunting ground, the equations shift dramatically. The eel's weapon doesn't need to be the most powerful. It just needs to interrupt your breathing long enough for the river to finish what it started. And out here, where visibility dies at arm's length and the current hides quiet pockets of depth, even a momentary loss of control can become fatal. What makes the electric eel compelling is that its threat emerges from evolution's quiet solutions. Low oxygen environments shaped it into a creature that surfaces to gulp air, living among waters too murky for sight to matter. Darkness molded its hunting strategy into a conversation of electricity and muscle responses. Its organs, stacked like natural capacitors, are reminders that biology can mirror engineering with eerie precision. And its accidental danger to humans illustrates a broader truth about the Amazon. The line between harmless and lethal often has nothing to do with intent. Here, survival rests not just on avoiding predators, but on respecting systems. The river is a conductor, the body is a circuit. When those two realities meet in the presence of an electric eel, the outcome depends on physics far more than on fear. And in the tapestry of Amazonian threats, that makes the eel uniquely unsettling. A creature that kills without hunting, harms without hatred, and forces you to confront the fragility of motor control in a world where water is always ready to rise above you. The rainforest floor is a restless landscape, even when it appears still. Beneath the canopy, the air feels heavy enough to settle on the skin like a second layer, carrying the musk of decomposing leaves, ripe fruit, and the faint ammoniac scent of animal trails. Light filters down in fractured beams that vanish before reaching the earth, leaving everything underfoot in a mosaic of shifting shadows. This dim world is ruled not by ambush predators waiting in holes, but by hunters that move, gliding through leaf litter with the certainty of creatures that rely on motion as much as venom. Among them, none is more emblematic of this restless ecology than the Brazilian wandering spider. Unlike orb weavers or tarantulas, it has no web, no burrow, no fortress. It carries its territory with it, patrolling at night with long articulated legs that can lift its body above the forest debris like a miniature wolf on stilts. Its cephalothorax shines faintly under moonlight, and every movement seems tuned to the slightest vibration: an insect wing brushing a leaf, a lizard's toes dragging across bark, the soft pulse of air displaced by anything living. The wandering spider's survival strategy is built on immediacy. It cannot afford patience. It hunts by contact, by confrontation, by seizing opportunities the moment they appear. This mobility is part of the reason so many humans encounter it. The same ecological traits that make dense understory attractive, humidity, shelter gaps, pockets of warmth, are also found in banana clusters, stacked firewood, abandoned shoes, and the corners of poorly sealed houses. When a wandering spider moves into these places, it is not seeking conflict. It is merely following the same environmental cues that have guided it for millions of years. But our objects become its hiding places, our floors become its nocturnal highways, and our hands become the accidental threats it reacts to with extraordinary speed. Imagine a house at the forest's edge. Daytime heat lingers in the walls, and cool evening drafts begin drifting across the floor. For a spider whose metabolism is tuned to the rhythm of night, this temperature shift is an invitation. It moves in, exploring crevices where heat accumulates and where insects also wander. A forgotten shoe near the door offers a perfect microclimate. Dark, insulated, safe. The spider slips inside, settling beneath the arch like a coiled spring waiting only for dawn to disrupt its stillness. Hours later, a person reaches for that shoe without looking. Contact is made. The spider responds with evolutionary precision. The bite itself is small, almost inconsequential in sensation. A sharp prick, followed by a rush of heat. Within minutes, the venom begins interfering with the body's electrical language. The wandering spider's neurotoxin operates on synapses, forcing nerves to release massive amounts of neurotransmitters while simultaneously blocking the body's ability to reabsorb them. The result is a kind of chemical shouting match inside the nervous system. Signals fire uncontrollably, muscles contract erratically, and the victim's sense of bodily control begins to fragment. Pain builds quickly, radiating outward from the bite like a spreading burn. The affected limb stiffens, then trembles. A dull vibration rises through the chest as the diaphragm struggles to maintain its rhythm. Breathing becomes shallow, then panicked. In severe cases, particularly in children, the elderly, or anyone whose respiratory system cannot compensate, this progression is terrifyingly fast. Clinical reports describe symptoms beginning within 10 to 20 minutes, with full systemic involvement soon after. Sweating, elevated heart rate, hypertension, muscle spasms, and loss of coordination create a physiological storm that can overwhelm even healthy adults if untreated. To understand why this happens, it helps to view the venom not as a simple toxin, but as a tool shaped by specific ecological pressures. The wandering spider hunts active prey, insects, frogs, small vertebrates, creatures capable of rapid escape. A venom that simply causes pain would be ineffective. It needs to interrupt function. Its neurotoxins evolved to induce immediate paralysis or at least severe motor disruption, preventing prey from fleeing into dense foliage. The side effects in humans, tremors, spasms, respiratory difficulty, are the byproduct of a weapon designed for quick immobilization rather than slow envenomation. In humans, the most dangerous consequence is respiratory failure. The involuntary muscles that manage breathing begin to misfire, either contracting too tightly or not at all. The lungs can still draw air, but they do so inefficiently, like bellows operated by an untrained hand. Oxygen drops. The brain compensates by demanding faster breaths, but the body often cannot obey. In this window, panic becomes both a symptom and an accelerant. A person struggling to breathe generates more carbon dioxide, deepening the physical crisis. Medical intervention is straightforward in principle, but time-sensitive in practice. Hospitals administer antivenom when symptoms are severe, alongside respiratory support and medications to manage hypertension and muscle rigidity. When treatment is available quickly, survival rates are high, and many bites result only in intense pain and temporary discomfort. But this optimism hides a geographic truth. Many bites occur far from well-equipped hospitals, in rural communities where transport is difficult and roads may be hours away. For a small child in these circumstances, the venom's impact can outpace the ability to reach care. Across Brazil and neighboring countries, the wandering spider holds one of the highest records for medically significant bites among spiders. It is not the most venomous creature in the forest, nor the most aggressive, but it sits at a dangerous intersection of behavior and biology. Its roaming lifestyle increases contact with humans. Its neurotoxin can overwhelm the respiratory system, and its size, often spanning 12 to 15 centimeters, ensures that its fangs can penetrate deeply. Fatalities are not common, but they are documented, especially among vulnerable populations. Each case underscores how the spider's evolutionary design, optimized for rainforest survival, becomes a medical emergency when transferred into human environments. Back on the rainforest floor, the wandering spider's presence makes sense. It is both predator and prey, hunter and fugitive. Diurnal birds and small mammals would devour it if not for its speed and defensive posture. When threatened, it raises its front legs high. A dramatic display meant to warn off attackers by exaggerating its size. In the forest, this bluff often works. In human homes, it is misread. People see aggression where the spider offers warning. The result is panic, crushed limbs, and defensive bites that were never intended to be part of the spider's nightly routine. Yet, the wandering spider is also a reminder of how ecosystems blur at their edges. As forests shrink and agricultural zones expand, the spider's adaptive flexibility becomes an evolutionary advantage. It moves along new corridors, irrigation ditches, plantation rows, stacks of harvested fruit, finding prey where humans create ecological disturbances. Banana shipments carrying spiders into warehouses and urban supermarkets are not signs of invasion, but of survival. The spider follows resources. Humans build over them. In the death index of the region, the Brazilian wandering spider occupies a high-risk tier not because it hunts humans or delivers inevitable fatalities, but because it embodies a confluence of factors that elevate danger. Potent neurotoxic venom, a roaming lifestyle that increases unintentional contact, and a bite capable of escalating into systemic collapse if medical care is delayed. It is not an executioner. it is a catalyst. Survival depends on response time, recognizing early symptoms, seeking treatment before respiratory fatigue sets in, and understanding that the venom's effects can evolve rapidly in the wrong circumstances. In the forest, its movements remain unseen, masked by the endless shuffle of leaf litter and the nocturnal pulse of insect life. In human spaces, it becomes a ghost at the boundary between wilderness and civilization. A misplaced boot, a bunch of fruit, a step in the dark. These are the moments when ancient evolution intersects with modern vulnerability. And in that brief collision, the spider's power reveals itself not as malice, but as a biological imperative honed in a world where hesitation can mean death. In the Amazon, where light fractures into emerald shards beneath an endless canopy, silence is rarely the absence of life. It is the presence of something watching. The undergrowth breathes with a slow, damp heat, vines hanging like cords between shadows, and every fallen log carries the smell of moss, decay, and the creatures that passed by in the night. In this dense, layered world, sound travels poorly and vision fails quickly. Hunting here demands a predator shaped not by speed alone, but by precision, patience, and immense, concentrated force. This is the jaguar, the strongest big cat in the Western Hemisphere, and the only one capable of killing with a single, catastrophic bite. Unlike its relatives in open savannas or rocky mountains, the jaguar is built for compression, short distances, tight spaces, and explosive ambush. Its shoulders are thick with muscle, its limbs compact but immensely powerful, and its skull disproportionately broad, housing jaw muscles that anchor deep into the zygomatic arches. Every part of its anatomy converges toward one function: to deliver more bite force, pound for pound, than any other big cat alive. Measurements of jaguar bite force reveal numbers that might seem unbelievable for an animal rarely exceeding 100 kilograms. Yet the results are consistent. This is a predator that can punch through caiman skulls, turtle shells, and armored mammal plates as though cracking fruit. Its hunting style reflects this specialization. While lions and leopards rely heavily on throat suffocation, placing their canines around the windpipe until their prey collapses, the jaguar bypasses that weakness entirely. The rainforest does not offer the clean angles or open leverage needed for a prolonged struggle. Here, a predator must end the hunt before the forest announces it. A jaguar's kill begins with a silent stalk, its rosetted coat breaking its outline into fragments of color and shadow. Even large males can move through dense undergrowth without disturbing a single leaf, each step calibrated to avoid snapping twigs or rattling palm fronds. Their approach along riverbanks is even quieter, paws sinking into soft mud, whiskers detecting microcurrents in the air, ears rotating independently to map the slightest rustle ahead. When the moment comes, the jaguar does not hesitate. It accelerates from near stillness into a powerful pounce, anchoring its weight onto the prey's back or flank. But the real kill happens in the next second. Its head swings forward with surgical intent, aiming not for the throat, but for the skull or upper neck. This shift in target is the jaguar's evolutionary signature, a hunting method so refined that it bypasses the messiness of blood loss or suffocation and goes straight for the structural core of life. The canine teeth of a jaguar are not just long, they are thick, conical weapons designed to penetrate bone. The upper canines descend like chisels between vertebrae, severing spinal cords, or drive directly through the brain case of animals many times the jaguar's size. Zoologists examining jaguar kills often find a single round puncture wound in the skull, an unmistakable signature indicating instantaneous death. Whether the prey is a capybara, a brocket deer, a tapir calf, or even a juvenile caiman, the principle remains the same: cut the system at its root. The speed at which this technique ends life explains why jaguars rarely fail once contact is made. Prey animals seldom have time to react, much less escape. A capybara struck by a jaguar's skull bite may drop instantly, legs buckling as the central nervous system shuts down. A caiman taken by surprise may resist with twisting rolls and snaps. But a deep bite into the cranial vault ends the struggle before it can escalate. Even armored reptiles whose skulls evolved to withstand enormous pressure cannot resist the focused force of the jaguar's jaws and the leverage applied by its neck and shoulders. For prey, the outcome is nearly predetermined. Unlike other predators whose kills can drag out, hyenas tearing, lions wrestling, wolves chasing until exhaustion, the jaguar's approach is clean, brutal, and efficient. There is no wounded escape story for most of its victims. If the cat chooses you and lands its bite, the battle is measured in seconds, not minutes. The jaguar's mastery of this technique is not limited to land. Along river margins, where caimans bask or surface to breathe, the jaguar becomes a semi-aquatic hunter. It slides into the water with barely a ripple, using the river itself as camouflage. Many of the most dramatic kills occur here. A caiman drifting too close to a shaded bank is suddenly pinned by claws and dragged upward. A sprawling turtle attempting to lay eggs is flipped and dispatched with a skull-crushing bite. A capybara, relaxed in water it considers safe, is seized from beneath. These attacks reveal how seamlessly the jaguar moves between ecosystems, an apex predator comfortable both in the tree's shadow and the river's murk. Human interactions with jaguars are rare, largely because jaguars avoid humans whenever possible. They are not man-eaters by tendency, nor reckless enough to hunt people except under exceptional circumstances. But the death index is not a measure of frequency. It is a measure of outcome, and here the jaguar stands near the top. If a jaguar decides to treat a human as prey, an event documented only a handful of times, the physics remain exactly the same. A skull bite delivered with the same intent it uses on caimans or deer would be unsurvivable. No amount of strength, weaponry, or adrenaline functions fast enough to prevent the kill once the cat is in position. This is the brutal simplicity behind the jaguar's ranking. It does not kill often, but when it chooses to, the probability of death approaches certainty. Its attack is not experimental, it is not tentative. It is a perfected evolutionary routine designed to eliminate risk and conserve energy. Prey does not struggle, prey stops. Yet the jaguar is not merely a killer, it is a keystone predator shaping entire ecosystems. By controlling populations of herbivores and mesopredators, jaguars help maintain forest structure, influencing the regeneration of plants and the flow of nutrients through the understory. Their presence regulates capybaras, preventing overgrazing along riverbanks. Their predation on caimans and turtles affects aquatic food webs. Even the threat of jaguars alters prey behavior, creating landscapes of fear that distribute animals across wider areas, reducing ecological pressure on specific sites. The jaguar's ability to hunt both on land and in water also gives it access to prey choices unavailable to other big cats, broadening its ecological footprint. It does not rely on a single environment, a single food source, or a single tactic. This versatility is one reason jaguars historically occupied an enormous range. from the southwestern United States to northern Argentina. But nowhere is their skill more evident than in the Amazon, where complexity rewards specialists and specialists rule the shadows. To walk through the rainforest is to enter the jaguar's unseen domain. The leaf litter muffles sound. The air carries moisture that amplifies scent trails. Trees rise like pillars in a cathedral of green, each trunk a pathway for quiet movement. A jaguar, observing from 30 meters away, might never reveal itself. Its patience is the patience of something that knows it is unmatched. It does not need to hurry. It does not need to roar. It watches, decides, and acts only when the odds are perfect. In this hierarchy of Amazon killers, the jaguar ranks near the absolute top, not because it is aggressive or common or prone to attack humans, but because its killing method is so refined that survival becomes almost mathematically impossible once the strike begins. No venom is needed, no constriction, no prolonged chase. The skull crusher of the forest relies on a single moment of contact, a single bite delivered with unrivaled power and precision. In the wet season, its tracks may wash away within minutes. In the dry season, its shadow may cross a riverbank without leaving a trace. But throughout the year, its presence defines the forest's upper tier of danger, a reminder that the Amazon's apex predator kills not through spectacle, but through the quiet certainty of evolution perfected. The forest at dawn hums with small lives. In the Amazon, that hum is not background noise, but the infrastructure of the ecosystem. Wings, legs, chitin, and moisture weaving a soundscape too dense for silence to survive. Beneath broad leaves and moss-dark logs, countless arthropods begin their daily turnover of the forest floor, and among them move creatures so small that even a careful observer might overlook them. Yet these bright flecks of color, yellows, blues, oranges, and the incandescent red of warning, hold in their skin a lethality that overshadows predators thousands of times their size. These are the poison dart frogs, micro-architects of chemical warfare, each one a living vault for toxins, potent enough to hijack the nervous system of any creature careless enough to touch them. The Amazonian wet season brings out a brilliance in these frogs that almost feels reckless. Rain beads on their skin, magnifying their color until each step becomes a flare against the dark leaf litter. But this display is not vanity. It is strategy. Aposematism, the evolution of bright warning coloration, exists here at its most unapologetic. Predators learn quickly. Anything glowing like a tropical gem is not a meal, but a mistake. Poison dart frogs are soft-bodied, small, and physically fragile. Their survival depends entirely on advertising the one attribute no predator can afford to ignore: the toxins parked inside their skin. These toxins do not originate within the frog's own metabolism. They are borrowed, sequestered, and refined from the tiny arthropods the frogs eat. Mites, beetles, ants, and especially specialized alkaloid-rich insects contribute to a biochemical library that the frog stores in glands beneath its skin. Each species of frog consumes a slightly different diet, resulting in distinct toxin profiles. Among these profiles, one compound stands at the peak of potency: batrachotoxin, one of the most powerful non-peptide neurotoxins known. The science behind this toxin is as elegant as it is catastrophic. Batrachotoxin disrupts sodium channels, the molecular gates that allow nerves and muscles to generate electrical impulses. These channels typically open just long enough to send a signal then close to reset the system. Batrachotoxin locks them open permanently. A nerve exposed to this toxin fires without pause, discharging signals in a relentless flood until it burns out. A muscle exposed to the same force contracts uncontrollably and then collapses. The body becomes a landscape of electrical chaos. When sodium channels stay open, the entire rhythm of the body collapses from within. Muscles freeze in tetanic contractions. The diaphragm, responsible for breathing, locks. The heart, dependent on precise electrical timing, begins to spasm. Arrhythmias spiral into cardiac arrest. Without ventilation or a rapid intervention capable of sustaining organ function, the victim enters respiratory failure, followed by irreversible heart stoppage. There is no pain tolerance threshold, no mental state strong enough to overcome what is fundamentally a mechanical malfunction. Once enough toxin enters the bloodstream, the outcome becomes a slow-motion collapse of every system the body relies on to remain alive. It is this predictable lethality that indigenous communities of Colombia, Ecuador, and Panama have understood for centuries. Hunters learned that even the smallest scrape of a batrachotoxin-coated dart could stop a monkey mid-leap or drop a bird from the canopy with a single hit. The process was delicate and deeply ritualized. Frogs were coaxed to release their toxins, often by gently heating them or allowing them to stress just enough to sweat out potent secretions. And these secretions were then applied to darts. Unlike venom, which must be injected, batrachotoxin can kill simply by entering broken skin or mucous membranes. Once applied, the toxin remains lethal for months. Blowgun darts tipped with these chemical weapons turned the forest canopy from a maze of agile escapes into a hunting ground governed by absolute advantage. To understand how profound this advantage was, imagine the physics. A monkey struck by a toxin-laced dart goes from full sprint to total neuromuscular shutdown in seconds. Birds fold in mid-air, their wings no longer capable of coordinated movement. Even large mammals hit by such darts may stagger only a few steps before collapsing. No poison the size of a speck should be able to end life so cleanly, yet batrachotoxin does so by exploiting the fundamental design of all animal physiology. In the wild, the danger extends far beyond the historical use of these toxins. Simply touching certain wild frogs can be fatal if the toxin contacts an open wound, the eyes, or the mouth. Ingesting a tiny amount, even the size of a grain of salt, can be enough to kill several adult humans. To hold a wild, toxin-loaded frog barehanded is to gamble with chemistry that does not negotiate. Captive-bred individuals fed diets lacking alkaloid-rich insects are harmless, demonstrating that the frog's poison is not self-generated but diet-dependent. Yet in their natural environment, surrounded by an abundance of alkaloid-laden prey, these frogs accumulate enough toxins to make their skin one of the most dangerous surfaces in the rainforest. The lack of an antidote is not a failure of medicine, but a reflection of batrachotoxin's molecular dominance. Once sodium channels have been locked open, no drug exists that can easily reverse the process at the scale needed to restore life. Treatment focuses entirely on buying time. Ventilators to support breathing, vasopressors to stabilize circulation, and relentless monitoring of cardiac rhythm. In remote forest regions, such intervention is rarely available. Those exposed often succumb before help can arrive. Even in modern hospitals, recovery requires extraordinary resources and a measure of luck. The toxin does not degrade quickly. The body must metabolize or excrete it over many hours while functioning at the edge of survival. In the death index of Amazonian creatures, poison dart frogs occupy the extreme end, not because they kill frequently, but because their toxin represents a biochemical certainty. They are among the only animals on the continent whose danger does not rely on strength, speed, or situational vulnerability. A jaguar must ambush correctly. A snake must bite and inject venom. An anaconda must secure its coils. But a poison dart frog needs only to be touched. A fraction of a milligram can end life without struggle, hesitation, or warning. Yet these frogs are not villains. They are integral parts of the rainforest's delicate architecture. Their toxins defend them from predators in a world where small animals rarely survive long without chemical or physical protection. Their diets help regulate arthropod populations. Their brilliant colors contribute to the forest's visual tapestry, marking territories, courting mates, and broadcasting evolutionary success. Even their lethality tells a broader ecological story, one of specialization, diet, coevolution, and the sheer biochemical creativity of the tropics. Seen from above, the forest glows with life, moisture rising like breath from the understory. But kneel beside a shallow pool in the early morning, and you may glimpse a frog no longer than a fingernail climbing a mossy root. Its body gleams like polished paint, rain droplets sliding off its skin. In that tiny, vibrant package lies a power that surpasses almost every other threat in the Amazon. It does not roar, strike, or chase. It simply exists, unassuming, beautiful, and, if mishandled, utterly unforgiving. In a world shaped by claws, fangs, venom, and muscle, the poison dart frog stands apart. It kills not through violence, but through chemistry so precise that survival becomes a matter of pure chance and proximity. In a rainforest defined by competition, it represents the smallest embodiment of absolute power, an organism whose size suggests fragility, but whose skin carries the capacity to end life at a scale the ecosystem has learned over millions of years never to underestimate. Dawn in the rainforest arrives without hurry. Light does not pour in. It diffuses, threading itself through the canopy in thin, drifting blades that touch the forest floor only after losing most of their strength. Down here, morning feels like an extension of night. The leaf litter remains cool, damp, and heavy with the scent of decay. Hidden within that mosaic of browns and ochres lies one of the least forgiving predators in the Amazon, a creature that thrives on stillness and surprise, turning patience into lethality. This is the bushmaster, one of the largest vipers on Earth, and perhaps the most misunderstood. Stretching well over 2 meters, sometimes nearer 3, the bushmaster defies expectations of snake behavior. Rather than coiling tightly beside open water or basking on exposed rocks, it buries itself in the clutter of the understory, where fallen leaves mimic its hourglass patterns so perfectly that even trained eyes often fail to detect it. The camouflage is not passive decoration. It is the foundation of an ecological strategy built around thermoregulation and prey movement. Warm-blooded animals, rodents, small mammals, sometimes unsuspecting humans, generate predictable pathways as they travel through the forest. Trails, game tracks, and human footpaths become linear corridors of heat. The bushmaster positions itself beside these routes not because it is aggressive, but because these lines of warmth simplify the equation of survival. In the early hours, when the forest retains the coolness of night, the snake's muscles operate at an efficiency suited for ambush. The bushmaster becomes a quiet sentinel, absorbing the faint vibrations of approaching steps through the substrate. Each footfall transmits a unique combination of frequency, mass, and rhythm. A rodent's scurry is light and rapid. A small mammal's trot is more deliberate. A human step is a seismic event. To the bushmaster, these signals unfold like a map of opportunity. When the right signature appears, the stillness ends. The strike is the purest expression of viper evolution. In a movement almost too fast for the eye, the bushmaster uncoils, anchoring its tail against the forest floor to channel acceleration forward. The head, already angled to maximize trajectory, snaps toward the target with explosive precision. Long fangs, some approaching nearly 5 centimeters, drive deeply into muscle tissue, delivering a volume of venom rare among pit vipers. The injection is not a drop, it is a surge, a pressurized dose of biochemical weapons evolved over millions of years to end struggles quickly. For an animal caught in this moment, the sensation is immediate and overwhelming. The bitten limb stiffens, pain radiating outward like a line of fire drawn through the veins. Tissue begins to swell within minutes, not gradually, but violently, as if the skin is being inflated from the inside. Beneath the surface, the venom is remodeling the body's architecture, destroying cell membranes, digesting muscle fibers, and rupturing blood vessels. Hemotoxins degrade structural proteins, turning solid tissue into a loose, bleeding mass. Anticoagulants ensure that this bleeding cannot be contained. Meanwhile, systemic toxins disrupt blood pressure regulation, driving it downward with catastrophic speed. Many victims, whether animal or human, attempt to flee after the strike, stumbling through brush or along trails as panic and adrenaline override logic. But the venom moves faster. Within half an hour, the swelling may become so intense that clothing or tissue compresses nerves, amplifying pain to unbearable levels. Dark bruising spreads around the bite as capillaries rupture. Bleeding at the gums or injection site begins. The body enters shock, a state where the circulatory system cannot maintain stable pressure. Without intervention, organs soon begin to starve for oxygen. Kidneys suffer first. Tasked with filtering damaged blood, they become overwhelmed by the flood of broken cells and coagulation byproducts. Acute renal failure follows, often within hours. This internal collapse is not dramatic in appearance. It is a quiet unraveling of essential functions. A victim may remain conscious far longer than they remain physiologically stable. Eventually, the combination of shock, hemorrhage, and organ failure leads to unconsciousness, then death. But behind this grim narrative lies the reality that determines most outcomes: location. Bushmaster bites rarely occur near towns or clinics. They happen deep in forest interiors, along remote logging roads, or on narrow hunter trails accessible only by foot. Even when a victim recognizes the severity of the situation immediately, the journey to medical care can be long and physically demanding. Transport may involve hours of carrying a person through uneven terrain, across streams or down muddy slopes. Every minute that passes gives the venom more time to dismantle the body's defenses. In clinical settings, treatment starts with antivenom, which neutralizes circulating toxins. But this is only the beginning. Patients often require intravenous fluids to stabilize blood pressure, pain management to control overwhelming nociception, and aggressive monitoring for kidney dysfunction. Those who arrive early may survive with significant tissue loss or prolonged recovery. Those who arrive late face far worse outcomes. The mortality rate in untreated cases remains extremely high. The combination of venom potency, large injection volume, and remoteness creates a scenario where biology and geography align ruthlessly. Yet, in its own ecosystem, the bushmaster is not a villain. It plays a vital role as a regulator of small mammal populations. Its hunting strategy reflects a finely tuned balance between energy conservation and ecological opportunity. Large-bodied predators like bushmasters cannot waste energy on pursuits. They rely on minimal movement and maximal efficiency. Their heat-sensing pits, specialized organs between the nostrils and eyes, allow them to map thermal landscapes with extraordinary accuracy, transforming darkness into a three-dimensional network of warm shapes. This sensory adaptation gives the bushmaster the ability to strike precisely even in total darkness, a skill essential for nocturnal hunting. The bushmaster's reputation for aggression is largely a myth. Confronted unexpectedly, it often tries to flee or remain motionless, depending on the situation. Its true danger lies not in deliberate attack, but in perfect camouflage and unfortunate timing. Most bites occur when someone steps too close or directly onto the snake, triggering a reflexive strike. The victim never sees the threat until the pain arrives. In the broader tapestry of Amazonian hazards, the bushmaster ranks near the top of the death index, not because it is common, but because a bite carries such severe consequences. Other snakes may strike more frequently, but few combine venom potency, venom volume, and geographical remoteness as consistently as the bushmaster. When it acts, the results unfold with a grim logic rooted in physiology and environment. Survival depends not on courage or physical strength, but on distance. The gap between forest floor and hospital bed, between venom injection and antivenom administration. In the quiet hours of early morning, as the forest slowly warms and insects resume their buzzing dances, the bushmaster settles once more into stillness. Its coils merge with the leaf litter, its pattern dissolves into the forest's textured floor, and its presence becomes a rumor whispered through the undergrowth. Trails that seem empty are anything but. Every footstep carries history, echoing along pathways shaped by countless animals before. Somewhere just beyond the next bend, unseen but perfectly attuned, the bushmaster waits. Not as a hunter stalking prey, but as a sentinel of evolutionary success. A creature whose patience and power define the razor-thin margin between life and death in this ancient forest. At the edges of the Amazon's dark waterways, the boundary between water and land dissolves into something ambiguous. Mud flattens into mirrors of stillness, reeds sway with barely perceptible motion, and the surface of the shallows carries the illusion of quiet. But beneath that calm lies the coiled architecture of one of the basin's most formidable predators. The green anaconda, heavy as a fallen log and supple as a river current, thrives in this world of half-light and silence. It is a creature sculpted not by speed or venom, but by patience, weight, and the elemental physics of pressure. The Amazon's flood cycle determines nearly everything about its behavior. As seasonal rains expand the river into a sprawling system of temporary lakes, drowned forests, and weed-choked shallows, the anaconda's hunting grounds multiply. These marshes are not random patches of water. They are warm, hypoxic basins where fish congregate, capybaras graze on floating vegetation, and juvenile caimans venture too far from their mothers. In this drowned world, the anaconda becomes invisible. Only a pair of nostrils and eyes break the surface, floating like misplaced seeds. The rest of its massive body lies suspended beneath, draped through submerged grasses and tangled roots. Anacondas are ambush predators of extraordinary specialization. Their bodies are not built for the long pursuit. They are built for the decisive moment when stillness shatters. The arrangement of the river bottom gives them perfect cover. Weed beds conceal the outline of coils. Muddy banks offer trenches where the snake can rest in near total invisibility. Even when fully submerged, the anaconda can anchor its tail around a root or buried branch, stabilizing itself against sudden movement. This anchoring is not incidental. It is the foundation of its killing strategy. The moment of attack is almost always a burst from below or the side. A capybara, lowering its head to drink, may sense nothing. A caiman, basking half-submerged, may register only a shift in the water tension. Then the anaconda moves, and the illusion of a silent river erupts into violence. Its strike is not the lunge of a viper or the snap of a croc. It is a sudden eruption of mass. The snake throws its body upward and outward, using its entire length like a spring. Its jaws clamp onto whatever it can anchor: neck, shoulder, snout, flank, anything that allows the coils to follow. Constriction begins the instant contact is made. Coils slide into place with mechanical precision, each loop powered by muscles arranged in a helical lattice that can exert crushing, coordinated pressure. Contrary to old myths, the snake does not aim to suffocate the victim directly. Constriction is far more efficient and far more devastating than that. Each time the prey exhales, even slightly, the coils tighten. Not because the snake chooses to squeeze harder, but because its body reflexively maintains pressure against external force. Breath becomes the victim's undoing. Scientifically, constriction kills by circulatory arrest. Veins collapse first, preventing blood from returning to the heart. Arteries soon follow, crushed under tightening loops of muscle and scale. Blood pressure spikes momentarily as the heart pumps into a system with no return flow, then plummets as circulation stalls. Within seconds, the brain begins to lose oxygen. Within a minute, consciousness fades. The lungs cannot expand properly, not because the snake crushes them, but because the diaphragm cannot draw air against the external pressure. Organ failure unfolds long before bones break, though fractures do occur when large-bodied prey thrash violently. This method is ruthlessly efficient for the anaconda. A large capybara may lose the ability to resist within minutes. A caiman, though armored and strong, can be overwhelmed if the snake secures a coil around the torso or neck. Birds caught along muddy banks never reach the air again. Once the animal's struggle weakens, the snake repositions, testing for resistance. If none remains, it begins the long process of swallowing, a task that may take hours and leave the predator motionless long after the initial violence subsides. Human encounters with large anacondas are rare but not mythical. Most happen when a person enters shallow water without realizing they've stepped into an ambush zone. The snake does not distinguish between species when it commits to the strike. It responds to movement, heat signatures, and proximity. Documented cases describe people bathing, fishing, or crossing swamps when they feel something clamp onto a leg or torso, followed by the unmistakable sensation of coils wrapping around their body. In these moments, survival depends almost entirely on whether help is close. A single person cannot reliably break a large anaconda's coils once they are secured around the chest or neck. The pressure is not uniform, it is dynamic, adjusting to the victim's breathing rhythm. The more they fight, the tighter the loops become. Every exhale gives the snake new leverage, allowing it to pull the coils inward by fractions of millimeters, enough to collapse vessels and prevent inhalation. Panic accelerates oxygen use, worsening the situation. Unless a second person intervenes immediately, prying the coils at the tail end or attacking the snake's anchoring grip, the outcome is nearly predetermined. Rare but documented fatalities reflect this grim reality. Victims who vanish in swampy areas are sometimes found days later, partially swallowed or abandoned after drowning. Others are rescued only after sustaining severe injuries from both the snake and the struggle itself. The common thread in these cases is isolation. Anacondas do not rely on venom or the luck of hitting a major artery. Their weapon is the cold consistency of force applied over time, and that force does not require precision. In the death index of Amazonian predators, the anaconda ranks high, not because it kills frequently, but because when it commits, it does so with near absolute certainty. A snake that weighs over 150 kilograms and stretches more than 5 meters does not need to be aggressive. It needs only to be patient. Ambush, mass, leverage, and physiology do the rest. Unlike venomous animals whose potency varies, or big cats whose kills rely on perfect placement, an anaconda's method is universal. It weaponizes physics. It turns the victim's own breath into a countdown. Yet in its ecosystem, the anaconda serves vital roles. It regulates populations of herbivores and aquatic predators. It shapes the dynamics of flooded forests where competition is fierce and visibility is poor. It thrives in an environment where stealth outweighs speed, where ambush is more effective than pursuit, and where the flood pulse creates unpredictable opportunities that reward relentless adaptability. As water levels recede and channels narrow, the snake retreats to deeper pools, conserving energy until the next inundation. During these dry periods, its body blends with sun-warmed mud, and the predator disappears into the landscape, waiting for the return of seasonal abundance. Its life is a cycle of hiding and erupting, vanishing and returning, an ecological rhythm as old as the basin itself. To walk through Amazon wetlands is to step into this world of concealed physics. Each patch of still water hides a story, each floating reed bed a possibility. A ripple in the shallows may be a fish, a caiman, or a muscular coil shifting beneath silt. The anaconda does not announce itself. It does not roar, hiss, or strike from a distance. It waits, coiled not just in vegetation, but in probability. And when the moment comes, it becomes an inevitability, a force that closes, tightens, and does not release until the forest's laws have been satisfied.